So good morning. Welcome once again to the last and concluding lecture in this series. This is lecture 3, conjugate beam method. Now in the previous 4 hours, we took a look at the basics of bending, flexure in beams. What is bending? What is curvature, change in curvature? What is bending moment? What is slope? What is deflection? What is shear force? And then we did simple problems. At this stage, we would expect you to be able to analyze any statically determinate beam, simply supported beam, cantilever beam, beam with an overhang, propped cantilever with an internal hinge, subject to any loading. And you should be able to find out the support reactions and draw the bending moment and shear force diagrams, and also draw the deflected shape and match the deflected shape with the bending moment diagram, so that the sagging region matches with a positive sagging bending moment, the hogging region with the hogging bending moment. We now come to the last part where we want to calculate slopes and deflections. And the method we are going to discuss today is a method which I think is not well understood by students. That method is the conjugate beam method. The first topic is an introduction. The second is the traditional way of finding slopes and deflections is by a conventional direct integration method. Then the other traditional method which is presently taught is called the moment area method. You may have studied that. In my view, that is not the method to be taught in civil engineering. A better method is there, and that method is conjugate beam method. This is a method practicing structural engineers use very commonly. We can also use the moment area method, but for many reasons I would say this method is superior. You can use it to solve indeterminate beams also. Plus it's more fun, it's more enjoyable. Moment area method is preferred by mechanical engineers. They don't even know about conjugate beam method. Conjugate beam method is sometimes taught at a higher semester, but my suggestion is to teach this immediately after teaching bending moments, because it's very simple, and after teaching the conventional direct integration method, and that is the idea in today's session. So you have applications to statically determinate beams, finding slopes and deflections, and also application to statically indeterminate. First, the introduction, and we begin by asking the basic question: why do we need to find slopes and deflections in beams? Is it not enough to find support reactions, learn to draw the bending moment diagram, and also the shear force diagram? Well, primarily that answer is correct because we are more interested in ensuring that a given beam can safely resist the applied load, or in design we want to proportion the beam so that the bending moments are within the allowable capacities and the shear forces are within the allowable capacities, the stresses are within limits. But we also need to find slopes and deflections. Firstly, we need to satisfy limits on deflection and sometimes on rotation. For example, a radar tower, a microwave tower should not deflect too much, otherwise you lose your transmission. But deflections, a beam should not deflect too much. It's psychologically discomforting. Look at that, heavy deflections are possible. And there are limits. For example, in a steel beam, the limit is span by 325. In a reinforced concrete beam or one-way slab, it's span by 250. There are short-term deflections in concrete caused by loading due to the elastic behavior. There are also long-term deflections, which we won't discuss right now, caused by shrinkage and creep. So if you model this gentleman standing on that bank, you would model it like this: a simply supported beam subject to a point load in the middle W, and we have a formula there, WL cubed by 48 EI. We can prove that, and we will prove that in today's session. It's going to know it and to ensure that that deflection is within acceptable limits. Well, the load is known, the span is given, E value is also fixed for the material. It could be timber, could be steel, could be concrete. The only way you can limit the deflection is by the I value, the second moment of area. And the deeper the section, the larger the I value. So E is elastic modulus, I is moment of inertia, area moment of inertia. The product is called flexural rigidity. If EI is high, let's say EI is infinite, then you say the body is a rigid body. It will not deflect, but there is no body in practice like that. There will be some deflection and there will be some rotation, but those should be so small that you don't see them. If the same load W is spread out uniformly as shown in the second figure, then also it will deflect, and it's important to know how much this will deflect. We'll prove that the formula is 5W. W here is the total load. So if your distributed load is Q, kilonewton per meter, Q into span L will be W. W will have the units of kilonewton. The formula turns out to be 5WL cubed by 384 EI. And it's nice to compare with this, so we must put both in with the same denominator. 1 by 48 also turns out to be 8 by 384, and if you compare the concentrated load case with the distributed load case, you notice that the ratio of this deflection to this deflection is 8:5. In other words, 60% more than had the load been uniformly distributed. It's also interesting to look at the maximum support reaction shear forces. Well, W by 2 is the maximum shear force at the support. That doesn't change. It doesn't matter whether it's UDL or concentrated. The bending moment is going to linearly vary here, and the maximum value is at the midspan, and that value is WL by 4. The maximum moment due to a UDL, the bending moment diagram is parabolically changing, and that maximum moment is WL by 8. So it's interesting to see that the concentrated load generates a bending moment which is twice that generated had the load been uniformly distributed. It also gives a deflection which is 60% more than the case where it's uniformly distributed. The second reason why we need to find these slopes and deflections is you have to take into account deformations when you deal with statically indeterminate problems, because the very definition of statical indeterminacy is that the statics, which is the support reactions and the internal forces, cannot be determined by simply applying equations of equilibrium. You can draw your free bodies, but you'll find there are more unknowns than available equations of equilibrium. So here we need additional equations. How many additional equations? Well, as many as you have a degree of static indeterminacy, which is essentially the number of unknowns minus the number of available equations of equilibrium. And those additional equations come from what are known as compatibility conditions, which means you need to know how to calculate the relevant deflections or slopes, and we'll see some example of this. Take a look at this beam. This is what we call a two-span continuous beam. Right? Let me make it more interesting. Let's say it's a log of wood and it's supported by 3 people. Let's say they are all of the same height, so they're all supporting at the same level. Had the middle person not been there, the 24 kilonewton would have been shared equally, 12 and 12 here. But certainly the middle fellow will also take some load. The question is how much? I'll give you many options. The three reactions, let's say, are 8, 8, 8 equally. That's one option. It satisfies equilibrium. Let me give you another one. Option B. 6, 12, 6. The middle fellow is in the middle, so he'll be carrying more load. Next option, and it will be true if the middle fellow was a short fellow not able to touch the beam, but this seems to be an obviously wrong option, but it's still satisfying equilibrium. 12, 0, 12. Fourth option, funny option, the middle fellow carries a load which is 2 times the external load, and the other two fellows are hanging onto it and pulling it down. This also satisfies equilibrium. So you'll find that in statically indeterminate problems, you can have multiple statically admissible solutions, but only one of them may be correct. So I want you to answer. I want you to guess which of these options, multiple choice, A, B, C, D, or E, none of the above. I want an answer. Answer is E, brilliant. So now I'll have a counter question to you. You're right. Answer is E. Now you have to answer this question. Okay, let's look at the middle support. Okay, look at this yellow answer here, 12 kilonewton. At least tell me whether the reaction at B will be greater than 12 or less than 12. Well, two choice only, greater or less. See, we don't know the answer because we know that VA plus VB plus VC must add up to 24. If you take moment equilibrium or apply symmetry, you know that VA will be equal to VC. We've got only two equations, we've got three unknowns. That's where the problem is. Now, we could guess that 12 seems to be a decent answer because this fellow is in the middle and the tributary area will spread half here, half there. So 12 seems to be a decent answer, but you said it is not 12. I'm asking you a simple question. Is it more than 12 or less than 12? Okay. Greater. Good. Good answer. Correct answer. And let me explain why it is greater. Well, first of all, the structure is statically indeterminate. It's indeterminate because it is over rigid. Over rigid here means you gave more constraints than the minimum needed for stability. So what we'll do something. We will cut the beam in the middle and separate out the beam. And then we will find that this reaction will be all equal and these two fellows should add up to 12. But when we cut the two beams, you'll find the deflected shapes will look like this, two separate simply supported beams. And you'll find that the slope here is anti-clockwise theta, while the slope on the right side is clockwise theta, and that violates compatibility. You can have only one slope. It could be 0, it could be plus theta or minus theta, but both should be having the same sign. So something is missing here. And if you look at the actual deflected shape, you can even guess it's going to take a shape like this. The rotation here cannot be clockwise or anti-clockwise because it would violate symmetry. The left half of this picture must be the right half as a mirror image. So the only way you can satisfy symmetry is by having a 0 value of slope. To have a 0 slope here, and to maintain continuity, you will find that you get something additional. The additional is a moment on account of the continuity, and the moment will cause it to hog, the moment alone, to such an extent that the theta that you get here is completely neutralized. That's compatibility. Now there are ways of calculating x, but don't bother. The moment you get x here, you will find that you will have a reaction here which is x by 4 up, x by 4 up, x by 4 down, x by 4 down. So you are sure that the middle reaction will be 12 plus 2x by 4. What is x? You need to solve. We'll see how that can be done. And that's the correct answer turns out to be 6. And we'll see this later that these are your answers. So option E should have been this, right? Let's proceed. Let's solve it by a slightly different approach, which is also good to understand. Now, in the previous example, the X, which is also called the redundant means the unknown, the extra force. Redundant means extra, which is unnecessary for simple stability. Let's say we will choose the support reaction at B itself as the unknown, redundant. So let's remove it. Let's remove this that support, and you're left with a simply supported beam. That simply supported beam is called a primary structure, and we will superimpose the external load W and the unknown reaction like this, and this plus this must add up to this. This beam is going to deflect by sagging, and this is going to hog, but the controlling condition, the compatibility condition is the support at B ensures that there will be no deflection. And we already know the formulas, we'll derive the formulas later, that this deflection is, remember 5 by 384, 5W by 384, but here if you treat this as L, you should put 2L the whole cubed. Similarly, the deflection here upward will be X into 2L the whole cube by 48 EI. Obviously, compatibility demands that these two must be numerically equal. You solve that equation, you get an answer, and if you apply it to the previous problem, you will find that X is equal to W is 24, L is 4, and you will get the same answer. That's the introduction. Now we move to an overview of the traditional way of finding slopes and deflection. Well, we begin by looking at beams. Let's take a cantilever beam. Let's say it's deflecting upward due to some reason. Reason could be temperature variation, differential shrinkage, could be caused by a load, an end moment for example. It deflects, let's say, upwards positive delta of X, and the tangent at that location X is called the rotation, positively marked, also called slope. It's a derivative of delta X, and the derivative of that rotation is approximately given by the curvature. Curvature is strictly 1 by R. 1 by R has a complicated formula like this, as I explained on the first day, but d delta by dx is a small quantity, and so this can be assumed to be equal to the numerator alone, which is the second derivative of deflection. Okay, that's it. Similarly, we have relations of the static variables. We saw this in the last class, and here also you have Q of X, the load intensity is given by the derivative of the shear force. The shear force is given by the derivative of the bending moment at any location. And there's a relationship between bending moment and curvature. You remember that? M is equal to EI times curvature. And curvature is delta double dash as a function of X. So this is a famous relationship, which you could write it in this manner. EI d squared delta by dx squared is equal to M of X. So this is one way of writing the basic differential equation for a beam. And you can also write it in this manner, because if you take the next derivative, you'll get, if M is this, next derivative, the shear force can be written as the third derivative of the deflection times EI, and the load intensity as the fourth derivative. So this is another way of writing it, a little more complicated, but at an advanced level, this is treated as a basic differential equation for a beam. EI d4 delta by dx raised to 4 equal to Q of X, and I told you that Q of X is generic, and with singularity functions you can handle concentrated loads as well. So let's compare. Static force quantities have these relationships, and remember I used ideas of grandfather, father and father, and these kinematic quantities have these relationships. I used the concepts of grandmother, mother and daughter. Well, if you have a load intensity, if you integrate it once, you get shear force. If you apply the boundary conditions, you can get an equation for this. If you integrate shear force, you get bending moment. Again, apply boundary conditions, solve for this constant, you have an equation here. And you also know, knowing this, you can get curvature. Curvature is M by EI. So you know curvature now. If you integrate curvature once, you get the slope. Again, apply boundary conditions. These boundary conditions are called kinematic boundary conditions. These boundary conditions are called static boundary. These are geometry related. If you arrested a slope like in a fixed end, then you say at that end theta is 0. Similarly, if you integrate the rotation, you get deflection, and that C delta is a constant here. So that's how you can do it. These are integral relations. You could find bending moments by integrating the load intensity twice and applying boundary conditions. Similarly, you could get deflection by integrating curvature twice and applying the boundary condition. Is it clear? This is a conventional method, and let's see how this can be done. Take a beam subjected to pure bending. It's a prismatic beam, span is L, flexural rigidity is EI. Let's see how we can do this. Well, it's nice to draw the deflected shape, and in practice we are interested only in the maximum deflection and the maximum slope, but let's derive an expression for delta and theta at any location x. So we begin with curvature. M naught is given, M naught by EI is phi, and so you have constant curvature, right? This is called the curvature diagram, M naught by EI. You can get slope by simply integrating it, and if you integrate it and expand it, it's very simple, M naught EI by into x plus C theta. Now you have to apply boundary conditions. What are the boundary conditions? Well, we don't know what's the theta at the two supports, but we know that at the midspan, the slope has to be 0, where the deflection is maximum from symmetry. So we apply that boundary condition, solve for C theta, and we find it's M naught L by 2 EI. And then we now have the expression for theta. It's an exact expression. We can even draw a graph. You'll find that there's a linear variation of theta. It makes sense because the derivative of your slope is your curvature. So this gives you a constant derivative. That's why, because it's a straight line, this is constant, or if you integrate this, you will get. Next, we integrate slope. Once you get deflection, and now you need to apply boundary conditions. What are the boundary conditions? Here you say that the deflection is 0 here and 0 here. So it's enough to take one side. We are actually writing an expression. So on one side you apply, you can find C delta turns out to be 0, substitute and you get an expression for deflection. It's a parabola. So it makes sense. We've done this for bending moment diagrams, remember? Remember that when the loading was uniformly distributed in a symmetry supported beam, the shear force diagram changed linearly and the bending moment diagram changed quadratically. Except that there, the normal gravity loading is negative and this got flipped over and this became positive. Now it's the other way. Right. And you can also substitute values to find the maximum deflection. The maximum deflection is where the slope is 0 and the slope is 0 at L by 2. You plug in that value and you'll get M naught L squared by 8 EI. That's your maximum deflection. Your maximum slope or rotation is at the support and it is M naught L by 8. Two simple formulas, but we can get at any location x both the slope and the deflection. Let's take another simple problem. Cantilever beam subjected to a concentrated load. If you've done this before, you know that the deflection is like this. The maximum deflection is at the free end and the formula is PL cubed by 3 EI. We'll prove it. So you write an expression for bending moment. How do you write that? Well, you can cut a section anywhere, draw the free body and you can write that. The curvature is simply the bending moment divided by EI. So you've got an expression for curvature. The curvature diagram is nothing but the bending moment diagram divided by EI. What is the unit of bending moment? Kilonewton meter. What is the unit of curvature? It's 1 by radius of curvature. So it's meter raised to minus 1. Very interesting. So that's the diagram. Integrated once, apply your boundary condition. Here the boundary condition is you're dealing with theta. At x equals 0, theta is 0 because that's your kinematic constraint. You plug it into this equation, and I'm going a little fast because my topic is conjugate beam method. This is something you have probably studied, and I just want you to enjoy the concept and see how this can be done. Remember, in practice, we are not really interested in equation. We want to know maximum, and that's where the conjugate beam method is powerful, but the conjugate beam method also gives you the same equation. We'll see how that unfolds. So you've got an expression for theta, integrate it, and you can draw it also, and you'll find that the slope diagram is like this, and if you put at the free end x equal to L, you'll find this will give you a slope of PL squared by 2EI. This is not a deflection diagram. The deflection diagram is here. This is the slope of this. So it's very nice to understand this in calculus. So when the curvature varies linearly, the slope varies quadratically, and you have a cubic variation of deflection. To get deflection, integrate the slope. You have a constant, you need an equation, you need a boundary condition. The boundary condition is at x equals 0, delta is 0, plug it in, you'll find C delta is 0, you've got your final equation. Very easy. And if you plot it, it will look like that. And if you put x equal to L, you get PL cubed by 3. Now there's something interesting here. Normally, this is what we've learnt in calculus. Where the deflection is maximum, the slope should be 0. In a cantilever, strange things happen. In a cantilever, where the deflection is maximum, the slope is also maximum. Where the deflection is 0, the slope is also 0. In a simply supported beam, where the deflection is maximum, the slope is 0. And where the bending moment is maximum, the shear force is 0 in the middle. Where the shear force is maximum, the deflection is the bending moment is 0. So it's a very interesting relationship. So in a simply supported beam, your calculus works beautifully. In a cantilever, it's all violated because this line doesn't have a point of contraflexure. So this curve will, if you extend this line, it will go on increasing. So the word maximum mathematicians use is different from the maximum that laymen like civil engineers use. So probably mathematicians will say maximum you should not use here. You could say largest deflection, which is correct, because this doesn't have a derivative, which can be 0. Okay. Now, practicing engineers want ready-made formulas. And so you can actually generate, using this method, standard formulas for cantilever beams, concentrated load. This is your maximum slope. This is your maximum equation or deflection. We just derived it. If you shift the load, say, to any arbitrary location, then this is the slope and these are your deflections. This is the deflection under the load. This is the maximum anywhere. Maximum will be at the free end. If you have a cantilever beam subjected to a concentrated moment at that end, you can derive this yourself. You can get the slope and deflection. If in the cantilever beam you have a uniformly distributed load, you get. All this can be derived, and the fastest way to derive this is conjugate beam method. And I want you to do this after as an assignment if you've really understood today's session. We look at simply supported beams. Similarly, you can derive these quantities. And remember, PL cubed by 48 EI, concentrated load, uniformly distributed load, 5 Q naught L raised to 4 by 384 EI, or 5 WL raised L cubed divided by 384 EI. Okay, that's it. Now we go to the conjugate beam. Listen carefully. This is a very beautiful method. We don't know who discovered it. It's not reported, but whoever did it was a genius. This is what was done. These are kinematic variables, we've looked at them. Deflection, slope, curvature. Basic variable is deflection, delta. The derivative of delta is slope theta. The derivative of slope is curvature phi, assuming that deformations are small. Look at the static variables. Bending moment is m, shear force is m dash, and load intensity is m double dash. In normal problems, this is given, load intensity is given, and you need to find out shear force and bending. In direct integration method, similarly, curvature is given. How do you get curvature? From the bending moment. But by the way, you can get curvature without bending moment also. For example, differential shrinkage, temperature. We look at one problem of that kind, and you integrate it twice, you get deflection. Clear? So there seems to be some similarity. In both cases, integration gives you the solution. So whoever discovered this method said, look, I've done lots of problem solving this. So why don't I use these ideas to solve this by using a kind of an analogy. The analogy is, in my real beam, I want to find out the slope and deflection given the curvature. So if I imagine a conjugate beam in which the loading is the curvature, that means the load diagram is a curvature diagram, and there itself you can recognize that you can't get point loads because curvature is never, curvature is always a smooth function, continuous function. So you will have only distributed loads here in your conjugate beam. In that beam at any section, if you calculate shear force, that shear force will match with your slope. So you calculate shear force in the conjugate beam, it will give you the slope in your real beam. If you calculate the bending moment in your conjugate beam at any location x, it will give you a deflection in that beam. So we pretend, we imagine that there is a conjugate beam, and if you load that conjugate beam, you will, with the curvature diagram, and you analyze it, and we are very good in equilibrium, we are weak in compatibility. Engineers are not strong in right brain, they cannot understand deflections and curvatures, so they can intuit it, but they are very good in equilibrium, they are very good in solving equations. So we know how to do this easily, and having mastered this, this is child's play, but we are doing it as an analogy. It's a lot of fun also. This is where this method scores over moment area method. Also, you can solve statically indeterminate problems of a certain kind. Let us see. So this is the link. So here's the definition. If we visualize an equivalent beam, an imaginary beam, but we've done lots of things in imagination. The whole virtual work method is imaginary. Virtual work is imaginary work, right? If we visualize an equivalent beam called conjugate beam with appropriate boundary conditions, that's important, with a distributed loading having an intensity Q of x, which is equal to the curvature acting on the real beam. This should be real beam, right? Then at any location x, the shear force V of x will be equal to slope theta of x in the real beam. The shear force V of x in the conjugate beam will be equal to the slope theta of x in the real beam, and the bending moment m of x in the conjugate beam will be equal to the deflection delta of x. That's a summary of what I told you.